biography and too many things. So I'll just
yeah, I copy pasted
this.
It's a bit. I think the biography was longer than the abstract.
So besides being my thesis external examiner, Hans is a professor.
And she did not cry.
No, that's still. I had still hope for my my research. So Hans is a professor at the Antwerp University in Belgium. He is the founding member of the Nexer Consortium on Cyber Physical Systems. And also he actually heads the modeling, simulation and design lab, which was founded by Hans at McGill when you were a professor at McGill. He's involved in several projects, big projects on modeling and multi-paradigm modeling from what I recall. There are so many other big projects. One of them is the Modelica, also project.
A small contribution to it. But,
So from what you can see, he has been involved in several groups and networks. I'll let you present yourself.
Thank you. Thank you for the invitation and giving me a chance of giving you a most appropriate talk. Notice the between quotes. No, whether this talk is appropriate, I don't know, but it is about appropriateness. Okay, and it's really about our vision that you should model everything. And as Ghislaine knows, what year was it? 2010?
2010, yeah.
Bel-Air's Barbados, you were there in April. So we've been organizing workshops all around the world on this topic, where we brainstorm on what would this mean to model everything. And of course, model everything means model everything explicitly using the most appropriate, and that's the rest of my talk, most appropriate what. By the way, the context is, maybe I should hide this, or if I can, I'll put it in a I don't know, I can put it like this. Okay, the context is the engineering of cyber-physical systems. And I was the chair of a European cost action. This is one of our meetings where we did some hand-on design of cyber-physical systems. And it was called multi-paradigm modeling for cyber-physical systems. And there we had the running definition that truly complex engineered systems, known as cyber-physical systems, are becoming common, and they emerge from the networking. So there's a notion of networking interaction of multi-physical, and this could be mechanical, electrical, hydraulic, biochemical, and so forth, and computational, control, signal processing, but also logical inferencing, planning, and so forth. These should be dots, processes often interacting with a highly uncertain environment, including human actors in a socio-economic context. So imagine these really complex systems with all sorts of requirements, including safety requirements, energy consumption requirements, and so forth. How do we build these in an appropriate way or in an optimal way? Well, as I said earlier, we will model everything. So I'll take a step back and introduce the notion of modeling, for as far as you don't already know what the essence of model is. Actually, it turns out that you can't say this is a model. This is some object that plays the role of a model. Yeah? So this is important. This could play the role of a model. And why would I model something? Well, it has to do with substitutability. I want to answer questions, maybe about an airplane. That is my system under study. This is the model of my system under study. It's a very naive model, but maybe there are certain questions about my system under study that I can answer using my model. For example, if the engines stop, will it fall to the ground? Well, here it has no engines, it will fall to the ground. So maybe it's a notion of substitutability. I substitute my system under study in a particular context to answer certain questions by something else, which we call a model, but this could also in another context be my system under study, and my model is a set of differential equations. So it's all relevant. So According to Stakowiak, there needs to be a notion of an original, the system under study, and then the model. There must be a reduction feature. It only makes sense to do this if we are only interested in certain properties of interest. And then we can use the model, but only for these properties of interest. And there is this notion of substitutability, usable in place. That's the essence of a model. And that actually, I want to add a little bit of terminology because I will refer to plant and environment. This is my system under study. It's a car. I observe the velocity. I have an embedded controller which controls the throttle, the acceleration. Oh, this should be a control acceleration, so that this keeps at a constant speed. Where do I get that constant speed from? Well, somewhere I have a button to set the V reference, the constant speed. But of course, the environment may be unknown. Maybe I'm going up a hill, I'm going down a hill. So this is an example of cruise control. But this is just to say that we always have a system and an environment. And the environment may be unknown or very diverse. The system is what we want to build, and very often in cyber-physical systems, there's a notion of a physical part and a logical software part. Okay, now back to the definition of model. Given the definition that I just gave a couple of slides ago, we have to remember that we're a bit, as engineers, software engineers, control engineers, we're a bit biased. We typically think that a model should be something in the computer. It is an abstraction, but this is also an abstraction. This is a clay model. The system under study is a car in the real world, but actually my model, or like this model also, it's something in the real world. And I do an experiment on something in the real world. Of course, this thing doesn't drive, and I can't ask how comfortable it is, if that is my property of interest, but I can ask how does the air flow around it. Okay. Now, so I have a real world system under study. Maybe I have traffic lights in the real world, and I have an automaton or a timed automaton to model it in the virtual world, in the logic-based world. But it gets really interesting if, well, this is also a known one where I have a logic-based automaton original, and I build an abstraction of this. So both of them are now logical or virtual. Yeah? But this is an interesting one. There are two. I have a project now on, everyone talks about digital twins, and you have to always be a bit contrary. I now work on analog twins. And in the 1950s, people used for ballistics and for flight simulators, they used analog computers. Because if I take an op-amp and I put a capacitor over it, this acts as an integrator. So you can take a set of mathematical equations, you can translate them to an electrical circuit, and then, well, physics will give you the solution. Of course, there is the supply voltage, 0 volt, 5 volt. And of course, if your mathematical solution is higher than 5 volt, it will saturate. But you can actually, this is an example of a board. Behind it are integrators, multipliers, and so forth. And this is actually the set of equations is in the form of wires. My project is about using much smaller field programmable analog arrays to do this. But this means that I have a set of differential equations, and my model is a physical electrical system. That's sort of the world upside down. Huh? Normally, it is some piece of software that is my model, a simulation model, and this is even more extreme and highly cited, by the way. This science paper. This is a Petri dish, and I don't mean Petri net, a Petri dish. And there is food in different places. And this actually models Tokyo and the surrounding area. And these are cities around, and they let a slime mold grow. And it does path planning. And after a while, you will clearly see the paths. And so this has been used to optimize the rail network in the Tokyo area. So that's really doing modeling in the physical world and simulation and optimization in the physical world. Okay, now back to less exotic examples, but you see what I mean. There's my system under study, there's the model, and the model can be used to answer certain questions about properties of interest in a certain context. Okay, now let's start with this appropriate story, because my talk is about appropriateness. The first one, actually it's number 0, because I will talk about appropriate abstractions, appropriate formalisms, appropriate views, and so forth. But what you should not forget is that number 0 is a valid model is an appropriate model. If my model is not valid, if this substitutability does not hold, it's nonsense. And as they say in the simulation community, don't fall in love with your model. We run simulations, wonderful. And then we do design space exploration. We use genetic algorithms to build variants of our model. We explore a design space with millions of models and we come up with the optimal one. And then we build it and then it's total nonsense. Why? Because our model was not valid. So this is Bernie Ziegler's picture. I have a real world entity. In a certain context, I call it a system. And within that context, I may replace real experiments by virtual experiments. If I build a model, of course, there are particular properties of interest. There is this context. And in that context, and with respect to the questions I want to answer, I can do a virtual experiment. So there's this substitutability, substituting the real system under study by a model and answering questions. But the problem is, this is something, you see this is an infrared camera. Maybe you can see there is a resistor there. And we do an experiment where the voltage, we are interested in, this is a Modelica model, this relationship V equals Ri, Ohm's law. There is a linear relationship between voltage drop over the resistor and the current through the resistor. Okay, now linear relationship, that's a straight line. Now we do measurements, and what you see is this straight line is indeed there. Each of these red dots is a measurement point. It is fine up to here, and then it starts deviating. Why? Because after a while, this resistor starts warming up. That's why you see now it's 25.2 degrees, but after a while you see it's 80 degrees. And then actually I have a video where after a while smoke comes out and there is no resistor. There's just 2 wires and the thing has burnt up. So obviously saying that Ohm's law holds is not true. It only holds in a certain context. And let me call it the validity range. Yes?
Silly question. Is it because the resistance changes?
Well, initially,
the resistance value changes with temperature.
Yeah, but which means that having it as a constant, yeah, you see there is actually a resistor, the resistance value, which is encoded with these colored rings, is actually at a reference temperature. And you can compensate, but it's still a parameter. Whereas in reality, it becomes a variable. So there are models, it's no longer Ohm's law, which actually describe the temperature dependency. Because of course, Ri square is the dissipated, is the power. And after a while, it will start warming up. And that's what you see here, indeed. But actually, we did similar experiments in another dimension. Here, it's DC. It's just a current, it's not a high frequency signal. We know that with higher and higher frequencies, the resistor acts as an inductor and a capacitor. So it isn't really a resistor anymore. It has other properties, and at very high frequency, there's a skin effect. Everything goes over the skin, over the outside. So when we say Ohm's law, we make so many assumptions which are often not documented. And then I feed this into my design space exploration tool, and it happily simulates and comes up with an optimal design, assuming that this holds. So this is a plea for watch out when you build a model. Also build a model not only of your component, but also of its validity range. And as some of you may know, I was very lucky to be in the original Modelica design team, the team that designed this language. And there were three of us, Alexandre Jandel from Gaz de France, Peter Mosterman later at TomaatWorks, and me, who wanted in the language, not only the model, but the person who builds the model should also write validity frame information, like when is this no longer valid? And this was voted away because, of course, the people who wanted to sell commercial tools didn't have that, so it never made it in there. But now we still have this problem that we now have a fantastic library with models, but that information about when they are valid is not there. Okay, so when I say model most appropriately, sort of level 0 is, yeah, be aware that your model always has a limited validity range and is always relative, not only to the context, but to the property of interest. All right, and so this is an attempt at showing this. I have my system in a context. I have a model of that system in a virtual context. I do an experiment. I have virtual measurements versus real world measurements. And validity is really saying, oh, I'm going to, from these measurements, calculate the properties of interest. So there's a possibly nonlinear transformation happening here. Here also I have virtual measurements. I calculate the virtual version of the property of interest. Then I have a distance metric. How far are they apart? And if that is smaller than a threshold, we say, yeah, that's acceptable. So, but so many things can go wrong. The modeler makes abstraction errors. There are parameter initial condition errors. There are maybe approximation errors. There are measurement errors and so forth. This is not an easy problem coming up with validity frames. We came up with this definition of a validity frame. And what is it? It is really the possibly infinite set of experiments, E, for which the distance D, that distance between the obtained computed properties of interest from the experiment carried out in the real world and the experiment carried out in the virtual world is smaller than a certain threshold. Okay, and the interesting thing is, this is called abstract, and invalidity is, of course, if it's larger. But abstract means that you have the abstract validity frame, you have the abstract invalidity frame. These are all the experiments for which it says it's too far away, and the union is the universe. And there's nothing in the intersection. But this is just theory. I cannot do an infinite number of experiments. What we have in practice is a concrete validity frame. It is the real experiments that I have done, and I have marked tick valid, tick invalid. And of course, that intersection is no longer empty. Sometimes we just don't know yet. Okay, and then comes an interesting thing. The fact is, we would have to do lots and lots of experiments. I'm going to show you a related story. This was together with Volvo construction equipment. They make these big construction equipment. I want to know, let's say I'm interested in a property and the property is related to safety. I want to know that if it breaks, it will stop within 50 meters. Okay. Of course, this depends on the road incline. It depends on the mass. It depends on the slipperiness of the road and so forth. Let's say I've done, and these are expensive experiments. No, I do the experiment even simulated, but also in the real world, they are very expensive. And you see, for a particular mass and a particular incline, maybe this particular combination says it's okay. If I have this combination with a higher incline but a lower mass, it turns out it doesn't stop in 50 meters. So that's the red zone. Now, there is a line, theoretically speaking, there is a line in this parameter space which divides the it's okay, it's safe from the it's not safe. We don't know that line. All we can do is do experiments. We do experiments. But we do know a bit about physics. We know that if I've done this experiment and I have a higher incline, if it doesn't stop in 50 meters with an incline like this, it will certainly not stop with an incline like that. The same if we increase the mass. If it didn't stop in 50 meters for this mass, a higher mass also won't. And so, of course, this assumes certain properties about that space, but you see, this is the inferred validity frame. We can infer through logical reasoning based on domain knowledge, we can infer more about where it's valid and where it's not valid. Okay. I have an entire collection of lectures on validity, so I'm going to stop here. But just to say that whatever follows that I tell you about appropriate modeling, let's first remember that the model has to be valid. If the model is not valid, all bets are off. And because you do design space exploration, you come up with an optimal design. But if you then check, the model was used outside the validity range. And there is this standard book by Oberkampf and Roy about verification and validation. And so they show it like this. This is the parameter. There are the parameters characterizing the system or the surrounding. Directing the system or the surrounding. Also, the environment can be characterized in here. I have this space, and these are experiments I have done. And let's say I somehow know that this is my validity domain. If I now have an operating domain, an application domain that is larger than that, well, here all bets are off. Yeah. And so, for those of you in automotive, there is something called ODD, in automated driving assistance, automated driving. There is this notion of, is this safe? And that's where this ODD, the operational design domain, is somewhat related to the validity domain. It really says, how are these two related? Yes, there was a question in the back first, and then...
Yeah, so this kind of figure or the validity is given for a given property.
Exactly. And so it is perfectly possible, and I'll come back to that when I talk about abstraction, because maybe for one property of interest, I can have a very simple model and it gives me the answer. For another property, I need an extremely complex model. The model that you use and its validity range are really dependent on the property of interest. Yes, indeed.
I have a second question.
Yeah.
I have the hand. The experimental results are given from the real statistical system or from the model?
That's a tricky question. The standard answer is we are comparing, verification is one thing. Validity is the real world versus the modeling world. Okay, so my first answer to you is we need to compare real world experimental data, real experiment with model data, with the results obtained, the real world versus the modeled world. That being said, remember I said the real world can be virtual. Okay, but let's not go there. Typically, validity is about the comparison with the real world. But now I'll give you another answer. So in principle, it's the real world versus the virtual world. The problem is this could be very expensive. Now, I once talked to someone at Airbus helicopter, the military helicopter branch. He spends 80% of his time, 20% he does designs, 80% he does calibration and validation. This is true in industry. I mean, otherwise you're flying blind, no? Well, literally, with the helicopter. But sometimes we can be clever. If I go online to buy a resistor, and I go to a catalog in my presentation about validity, my full presentation, I have pictures of this, or you buy a spring and you go to a catalog, thousands of springs you can order from a supplier. They will give you the law. They will give you Hooke's law for the spring. They will give you Ohm's law, and they will tell you the operating conditions. They will say this law, but we only guarantee it in this temperature range, in this voltage current range, and so forth. So sometimes it is the supplier who gives us the guarantees. So we don't have to do experiments. Although our experience is like you buy an electromotor, they have the specs, we do the experiment, it's not true. So ultimately you do have to do some testing. Another often used trick is Typically, the models we use, or at least I use for physical systems, are lumped parameter models. They're differential algebraic equations. They assume that the density is uniform, the material is uniform, and so forth. So you can see this as a point mass. Now, in reality, maybe that's not true. Maybe that is too much simplification. So what I'm doing is, to do my validation experiments, I will not do the, okay, here's my model, differential algebraic equation. Here's my real thing. I don't do my experiments with the real thing. I build a finite element model of this with the geometry, and then I give the material distribution, and I start from first principles, really first principles. So these are partial differential equations. Takes a lot of time to simulate, but their validity frame, because it's first principles, are extremely wide. It's almost as if I have reality. So this is something that is often used. You replace the experiments in reality, which are sometimes not ethical, blow up a bridge or whatever, things that are just not possible. Then you do it with these very, very detailed first principle models. And that way, I don't have to do it in the real world. So my first answer is, it's always real world versus virtual. My second order answer is, but sometimes I can replace it by another simulation, but one with a very, very detailed high fidelity model. Yeah, because of course, reality is always reality. Yeah? And it will always, even these first principle models, let's say I take this and I have a first principle model. This will have a huge validity frame. But if I take it to the heart of the sun, these partial differential equations, this is now at a completely different atomic level that the forces are happening. This is no longer valid. So there is there also a limit, but for all practical purposes, this is useful. But then you get these interesting, I talk to people in different industries, and for example, Volvo, they find for anything thermal in the engine, it is so complex to simulate that it's actually faster to do the real world experiment. So that's sort of, for a long time, I thought it was always faster to run the simulations, the detailed simulations. But they say, no, we would rather do the real experiment. Okay, yeah. And you also had a question?
Targeted in the same direction, I guess, but so far validity is here, like Thomas variable. So the model is valid or not valid. I was wondering if it also makes sense to consider a continuum.
Absolutely.
Say,
yes. So first of all, you can look at sensitivity. If I look at this, for example, I may be willing to use that simple model up to here because it doesn't deviate too much. And what I mean by sensitivity is how rapidly does it go off? Maybe this stays close. So you can look at sensitivity. And of course, whenever I notice that my model is not valid, I have different options. Maybe the resistor, it is not valid, and I use it in a design and I see the design is wonderful, but it doesn't work because I'm using the model outside its validity range. So what I do is I take that resistance and I replace it by 10 resistors in parallel. So I change my design and now I get the same resistance by putting them in parallel, but each of these stays within their validity range. That's one option. What is the other option? The other option is, of course, I could build a model of what is happening here. And of course, you know what is happening here. Here, all of a sudden, I have two wires. So here it is still a continuous function. At some point, you just have two wires. That's probably not very useful, except, you know, the old circuit breaker in old houses, it was just a wire. And if the current is too high, it melts. And you have to, that is a functional requirement. And so sometimes this is actually useful to use it in this range. So never say this is useless. There's probably some application for that. Yes. But you're right. And there's the whole question of how can we characterize this? How far can we go with this?
and it's also the threshold itself, like in for instance, in statistical experiments, we also have this threshold of 0.05. That's completely
But you see, I have an entire keynote, lecture, tutorial. I have them all on validity. There are all these tests you can do, and many of them are statistics based. Yeah, indeed, this goes very far. And of course, Oberkamp van Rooij, I mean, it's a 300-page book, no? And it's all about how to do validation. This is nothing new. What we are trying to do is to provide tooling so that model databases not only contain the model, but also contain a model of the validity range, so that if I automatically search for an appropriate model, it will weed out the ones which are not good for my property of interest, which are not good outside a certain range, and so forth. So this is the thing I'm trying to do. Yes.
Yeah, as a follow-up, because I have another question.
Yeah, sure.
So is that something that specifically in computer science we need to be more aware of, that when we create a model, we also set the conditions for when the model is? Because in my understanding, in mathematics, for instance, they do that already. If you have this test, they tell you exactly when you're allowed to use it or not.
Yes.
So it might be just our domain was a bit behind.
I think the problem is that, especially in computer science, very often the real world is a bit ignored. And so we live in our assumption that there is this perfect abstraction, logic-based abstraction. But for example, ultimately, our logic is implemented on digital electronics, which is implemented on analog electronics. And there are lots of examples where if the battery power goes down, well, in the limit, there is no battery power, you have no computation at all. Is that in our semantic framework of our programming language? It's not there, no, but it should be. And the people who are in performance modeling, for example, and safety modeling, they do take this into account. So I think it is mostly a problem in computer science. And when computer scientists start helping with design space exploration tools, start helping engineers, that sometimes it's forgotten that we are dealing with models, and models have a limited validity range. But of course, also when I said substitutability, what do you think of? You think of Liskov. In computer science, we have Liskov substitutability, and this is related to subtyping. And of course, we have types. So this is something like a type, you could say, this region in which it is valid. But of course, it's a bit more complex if you do it with highly nonlinear physical systems than if you do it with a function, for example, and a function that is based on discrete. Okay. So maybe I will speed up a bit well, I'll come back to this. By the way, this is me when I was a PhD student on the Modelica design team. And this is Hilding Elmquist, who in his PhD, we were discussing how many decades it takes before your research idea has a practical impact. Hilding Elmquist's PhD at Lund in 1979 introduced equation-based object-oriented modeling and a language called Daimola. Then so many years later, in the early 90s, this is early 90s, we had Modelica. Now Modelica has a huge following and many companies support it. There's open source, open Modelica implementation, and so forth. 79 was the original idea. It takes a bit of stubbornness and a lot of time. But anyhow, I was lucky to be part of that team. This is Peter Fritzon, who built Open Modelica. And you could argue that this is an appropriate language for modeling lump parameter models. But is this appropriate to model the validity frame? As I mentioned, 3 of us were trying to influence the standard when we made the standard, and we were outvoted. But now this is coming back. People are realizing you need to explicitly, I'm finally vindicated, no? You need to have explicit representations of validity. Okay, now this was...
It's just like you're doing mathematics and you do some reasoning and you don't state any hypothesis, anything. That's the reason.
For example, c squared equals 4. What is c? Mathematically, c is either +2 or -2. This is also a story of domain-specific modeling. If I tell you C is the concentration of alcohol in beer, concentration is non-negative. You can't have negative concentration. So if I have that knowledge, I know that one of the two mathematical solutions is nonsense. And so these things, indeed, we need to, the MathWorks did this very cleverly in the domain-specific modeling. But yes, indeed, we need to be explicit about everything, and in particular, these domain constraints. So this was number 0. And now I know you're all convinced that models should not just be used blindly. They have to be valid. So you always have to have the reflex, but this is valid. Now, most appropriate abstractions. You already mentioned it. It's an abstraction. A model is an abstraction. The fact that we choose particular properties of interest means that there are other properties of interest we are not interested in. And so maybe we can build a relatively simple model to answer our questions, and it will be valid. Okay. Now, this is a paper some years ago at WinterSim 2019. It's a very naive representation, but it was an agent-based simulation of traffic, of cars moving around. See cars moving around in a city. Now, if you do an agent-based simulation, one of the problems is you have lots of agents. You have thousands of agents, and they're all moving around. Now, maybe the way I looked at it initially was I want to speed up my simulation. Now, what if I have a jam? The red circle identifies a traffic jam. What is a traffic jam? Cars are together in distance, and they all have the same velocity. They move as a jam. Maybe I can do something called adaptive abstraction. I can, during my simulation, I can identify these, and now I simulate not just cars, but also jams. And maybe there are 50 cars in a jam. I replace the cars by a single jam. That's interesting. All of a sudden, the complexity of my simulation goes down, but it has to be valid still. I can't just abstract and get completely different results. The idea is that I do an abstraction, but I simulate, but I still get the same answers as I got with my more detailed model. Yeah. Okay. Now, I was at NIST, National Institute for Standards and Technology in Washington, and they said, this is interesting, but not for your reason. We have infinite hardware. We don't care about performance. Yeah, but they pointed at something which I found really interesting. They say if you move between levels of abstraction, you can give different explanations. You no longer give an explanation why is traffic so slow in terms of the individual cars. You can now say, there are more than 5 jams. So you go to higher and higher levels. So these abstractions also allow, for example, to managers, explanations which are easier to understand rather than these very low levels. So from now on, you do multi-abstraction for performance, and you do multi-abstraction for insight and explainability. Now I'm going to draw, we did some experiments, of course, in the discrete event world, but also in the physical world. Here you see, this is a model of a resistor. This is a delay line, a transmission line, and it consists of little blocks in which you have an inductor, a capacitor, and a resistor, and another resistor. Because if I send a high-frequency signal through there, there are all these inductive and capacitive effects. But it turns out, if it's a DC voltage that I'm sending in, or a very low frequency voltage, it's enough to have a very simple, or I think a very simple model. Yeah? And so maybe I can, depending on the context, I can use a different model. Of course, they must all be valid. Meaning, if I do the real experiment, I get the same answer about my property of interest. And this is a more, how would I say, abstract view of things. And now we come to language engineering. I have a model in some language, F, a formalism F. Now, I can look at the semantics. For example, this is a differential equation. The semantics gives me a trace. The solution, given initial conditions, parameters, and inputs, signals, it gives me the meaning of that model. Okay. And then from the meaning, the trace, I can calculate maybe total energy dissipate or efficiency. Right? If this was a model of a physical system, I simulate, that gives me the semantics, and based on that, I evaluate my property of interest. And then I have a question here. I only have true or false because I want to know, is it energy efficient or not? Okay, so in this case, true. What does abstraction mean? Abstraction means in this modeling world that because we're modeling something in the real world, we're assuming that this is a valid abstraction, a valid model. Now we do an abstraction. Now we have the abstraction of that model, possibly in another language. Maybe it's an automaton. It was a differential equation. We see certain modes. We abstract. We have an automaton. We have the semantics of the automaton formalism f prime, which gives me a trace. And over that, I evaluate my property. Okay. And again, I have the question, does the property hold or not? I get true or false. What is the mathematical definition of abstraction? The mathematical definition of abstraction is an implication relationship. It says, if on the abstract model, I ask a question and it gives me true, this should all imply that if I were to do the more expensive, detailed exercise, I must get the same answer. And it also means if I had false here, it must give me false there. That's the essence of abstraction. And that's, of course, the basis of substitutability. I substitute this detailed model by a less detailed model, which is faster to evaluate. And I have substitutability. And this brings me to, and you see, this is low performance, this is high performance. That's typically why I would do it. But then, of course, at NIST, they said, but also you can give, from a cognitive point of view, you could reason at a higher level, and maybe that's easier to understand by managers, for example. And now this looks a bit weird, this potato-shaped object. This is my detailed model, and when I simulate it, it gives me this trajectory. This potatoid is the validity range. Okay. Now what I do is I detect at some point that if I simplify the model, I can simulate it, and you see the dimension has been reduced. I can simulate it with a simpler model. This is the semantics of my simpler model. But of course, that simpler model doesn't have so wide a validity range. So when I go outside, I have to go back down to a more detailed model. And here I continue. So this is the story of multi-abstraction. And this can really be used in many contexts. You see here, the upper one is the simulation with jams, and here it's with cars. I should say the really difficult part is this here, is coming back and reinitializing. Because this is aggregation. I collapse the dimensions. So the trick is here to have every jam carry in it, and it is the dynamics, a distribution of the velocities of the cars in the jam. And over time, the distribution evolves. The state of that jam evolves, but it's a distribution. And if it becomes too flat, that means there is too much of a spread of velocities. We know that we've reached this point. And then I'm going to sample from that distribution, and I'm going to reinitialize cars with different velocities. So this is an anecdotal example, and that's the art, of course, of doing multi-abstraction modeling. How do you go back? That's not obvious. Okay.
So the jam, when the speed reaches a certain level, it stops being the jam.
When the distribution of the speeds, if we're in a jam, we all are in a limited location, we move, but we're together, and our velocities are almost the same. And you could do it actually also with the space, but we do it with the velocity. If the velocities start deviating more and more, it means the one in front with a high velocity will shoot ahead, and that, of course, is no longer the So that's how we do it.
How would you go backwards? Because essentially going up is easiest. It's a projection, so I just discard information. But once you want to go back to your more wholesome mode, do you have a random distribution?
So the trick is that the dynamics of your more abstract model has a complex state. It somehow still captures the distribution of the speeds. So along this evolution, I evolve the distribution of the speeds. So my transition function, which has the dynamics of the jam, because the jam moves. The jam moves from here to here to here. You could say a jam is just a single point. No, it's a point and it has a velocity distribution. And we evolve the velocity distribution. And now to go back down, from that velocity distribution, I sample velocities and I initialize my individual cars with these sampled velocities.
Okay, but then I say going downwards, you also have a validity consideration to make there, because it's not just model on top or below, but it's also transitioning between the two. This valid.
Well, you see, validity is about a model.
Yeah.
And I would rather call it consistency, vertical consistency, because this model must be valid. Because, okay, you see, here's reality. This is validity.
Right.
This is validity. This is some kind of consistency. But of course, it's a triangle. What we are saying is, if I come back down, this must still be valid. This must still be valid. Because ultimately, so I could simulate it at this level. I could simulate it at this level, but only in this operating range. Both would be valid. But what if I now do dynamic abstraction? The whole thing, during the whole simulation in this case, it must be valid. Now, of course, when I'm here and when I'm here, that must be valid. When I'm here, that must also be valid. So indeed, there is always the link with reality. And that it is my problem to encode these two in such a way that it remains valid. But this relationship in the case of deployment, which is not really, I have a function, I have a controller. You're a control engineer, you've designed an optimal controller. You have proved that it keeps your system stable. Then I implement it in an embedded system. I have a CAN bus in a car, I have buffers, I have maybe a little operating system, OSEC or so, and then the real world happens. I cannot meet my deadlines. So even though it was proved to be correct, once I deploy it, which is not really refinement, it's something else, it's deployment. This may no longer correspond with this, the properties that held there no longer hold. And so that is called vertical consistency. They need to be consistent. Yeah. But I'll say something more about consistency in general a bit later. But yeah, it's this itself, if you start applying this in different domains, it's really exciting. But it's an art. Finding like using that distribution, these are tricks to make sure that I will be able to go back down and that it is still valid. All right, most appropriate notations, this is the one we all know, and you probably know this. Who has read this paper? Moody. No? Daniel Moody. Some people, it's called The Physics of Notation. And it's mostly UML bashing, but okay. It's about the notations. But what is nice is, he says, you have some notation. You have a diagram creator who wants to send a message. I scribble something and you read it. Okay. We do an encoding in a diagram and the receiver decodes it. Will the intended message arrive 100%? It depends on how I encode. It depends on how this decoding happens. It depends on the channel. The channel, look, my colleague at McGill, Greg Dudek, built this underwater robot. At Bel Airs, exactly, that's where do you do experiments? They do experiments up north in Quebec in a lake, but it's much nicer to do this in Barbados. No? Yeah. So, but anyhow, they want to communicate with this robot. How do divers do it? They have a language, like everything's okay, up, down. You notice that these hand movements are all very different, because underwater there is a lot of turbidity. It's this channel is noisy. So it's not easy to communicate, and it's dark and so forth. So you need a language with symbols that are as easy to distinguish as possible. This is just information theory. So what they did was, and they have a paper about this, they made encodings. You see, they have these pancartes with 9 by 9 or 5 by 5 black or white blocks. And this is what they want to transmit, 5. And this is what it looks like for the underwater robot. They had a model of the water, how it filters a visual signal. They had a model of the vision system, and they basically did an optimization. They solved an optimization problem. What is the optimal encoding of a set of so many codes? Yeah, symbols, yes. And they found an optimum. Of course, it all depends on their model of vision, on their model of the water, the noise, and so forth. But they came up with an optimal encoding. And as you can imagine, humans can't read it, but the symbols are far enough apart to have a good signal-to-noise ratio. Okay, now this is communication between a human and a computer. Possibly between a computer and a computer. But what about if we want to communicate, we want to design a board like this, or we're designing a visual domain-specific language. This is called semantic perversion, because it says stop, but it's green, and green means go. So this is a bit strange. So this is probably not good. You should have semantic transparency, as he calls it. We've had a bit of fun. We've learned that we built a tool, a meta modeling tool, first Atom 3, then Atom PM, for generating modeling environments. Okay. But after a while, we noticed that in industry, people are a bit reluctant to use this. Oh, you're a university, who is going to support this? So what we started doing, we use, maybe you know Draw.io diagrams. It's web-based. This is Draw.io. But we hacked it a bit to have domain-specific notations. And if you make a connection, it knows that if I connect this to this, it should be blue, and the port should look like this. So we needed workflow models. And you can see this is a bit like an activity diagram. No, these are activities. This is the control flow in blue and thick. This is the data flow. These are artifacts coming in, artifacts going out, and they are in thin green lines. So we did this little exercise trying to apply Moody's principles of what is the most appropriate notation. For example, this is green and thin line. This is blue and thick line. So it's easy to distinguish what is control flow and what is data flow. But you see it there, it's hard to read. But we found now that recently we've been using Draw.io a lot to design domain-specific languages, because people in industry like this. It's an existing tool. They can always fall back to it as a drawing tool, but we give them domain-specific editing support. But the reason why I'm showing you this, that's just a side remark, is because we had fun applying Moody's principles. He has a set of 10 principles of what is the most appropriate notation to what is basically activity diagrams. Okay. Notation. Notation is just a concrete visual syntax, is just a special case of syntax. What is the most appropriate formalism? And by that, I mean both syntax and semantics for a particular problem. I would argue that Modelica is an appropriate, of course, I have to know. The beauty of Modelica is, first of all, it's multi-physics and also logic, PID controller, electrical, mechanical. So it's closer to the mental model of the user. And what is most important, it's mathematics-based rather than computation-based. This is Simulink. You have an input, you have an output. Here I just have V minus Ri equals 0. If I know I, then I can compute an R, I can compute V. But if I know V and R, I can compute I. the physical world doesn't know about how to compute. The physical world is made up of constraint laws. So these languages like Modelica are called equation-based object-oriented languages. Oh, and by the way, I think you had a question a while ago, and I forgot about your question.
Yeah, my previous question already answered this about going back and fundamentally you will use information.
Yeah.
But for this, do they have the same validity then?
The bad thing about Modelica is it has assertions, but it does not have an explicit representation of the validity range. You may put some assertions in there, but it's not really what I would call a validity frame. So this is one of the things we're working on now, but it's not in the language itself.
But in general, when you do mathematical modeling, your validity range is
the mathematical domain.
It's different from when you do simulation.
Yes. But you see, when I do mathematical modeling of a physical system, hence my example of c squared equals 4. Yeah, mathematically there are two solutions. In the chemistry or physical world, there is only one solution. So, which actually means that c squared equals 4 is not the right formulation. It is c squared equals 4 and c larger than or equal 0. So there's some inequalities there. So that's a way around it. But even then, that's even not validity. That's just using an appropriate language, not just mathematical equations, but also inequalities. That is the right formalism to model my physical system.
So I would guess Modelica would let us answer more questions, but with less certainty.
Yeah, I think the advantage of Modelica is it is closer to our domain, our application domain, and a lot of the things you would have to do by hand are done for you by the compiler. It uses computer algebra to rewrite and so forth, and finally comes out a piece of code which you can run. But there is still the problem that these are continuous equations which need to be discretized. So you need to ultimately use a numerical approximation. And so when we talk about validity, do we talk about validity of the mathematical equations of the modeling the real world? Or do we talk about the discretized mathematical equations with the numerical error, with a certain step size? And ultimately, that is what counts, because that's what is giving me my simulation results, and which let me make maybe wrong decisions. So it's actually quite complex, because we think about it as if it's equations, but it's not even equations. It's a discretized version of the equation, which run on a computer with a 64-bit IEEE 754 floating point and so forth. All of this has influence on what I actually finally give as an answer to my question. And this is also something which, at least as a teacher, we try to explain to students, be careful. There is a big difference between what happens in the real world and your mathematical models, your simulations, your programs, and so forth. And we should not think that the world is mathematical. Okay, maybe some of you know this picture. It's a very old picture by a company called MetaEdit Plus. MetaCase, they have a tool called MetaEdit Plus. And when we talk about most appropriate, the ultimate most appropriate is, you saw it here also, I'm actually using a notation which is very close to our mental model of the real world. This corresponds to a spring. This is inertia, but rotational inertia. There is well, maybe this one was better. There is a bearing, there's an axis, there's a resistor, and so forth. This really, there is a one-to-one relationship. This is called structural validity, by the way. This is not absolute validity. If we see the structure of our model, and it looks that there is a morphism with the real world, we will have more confidence. Is that a better model? Is it valid? I can have a neural network which I train, which has a very strange internal structure, which does not reflect reality, but maybe it is a valid model. Yeah? So there's different kinds of ways of reasoning about validity. Okay. Now, anyhow, I'm going to, this is a conference registration system. I'm going to model it. And I'm modeling it in a domain-specific modeling environment, which is generated using MetaEdit Plus. There's a splash screen followed by a choice. Depending on the choice, you go to a registration page, you go to a combo page, and so forth. This indicates start, this indicates stop. Here, this means send an SMS to register. We all can easily understand what this means. There is a certain control flow. There are certain screens that are shown. Sometimes I can type something in, and so forth. If I have the right tooling, I can press the button and out comes this application. Possibly for different platforms, on an Android platform, on an iPhone platform, and so forth. So you could argue that this is more appropriate than writing it in Java. Okay, why? Because it is mentally closer to the user's image. Yes. You had a...
Yeah, you're almost making the case that in any case, a DSL is more appropriate.
No, yeah, actually, I know I'm exaggerating a bit, and I was going to come to it later, but it turns out there is, I forgot his name. He's a French guy who was working for Panasonic, and he wrote a paper. It was about domain-specific modeling in the trenches. And but I forgot his name. It's a paper from 15 years ago. And Panasonic was going to use, or were considering using domain-specific modeling. So they had two teams, one using component-based software engineering, another using language engineering, DSL. And they built home automation systems. The lights go on and off, the blinds go down, the temperature is regulated. And they really nicely showed that there are cases where it's better to do it with component-based, and there are cases where it's better to do it with domain-specific modeling. And that actually is then again linked to product families. Do I use feature models which have a sort of hard-coded variability, or the ultimate variability is domain-specific models? There I can change the structure much more easily. So indeed, it's not so black and white. All I'm saying is this is an example of taking a step back and thinking what might be the most appropriate notation. And the answer is, it depends. And then you do studies and you see that for certain problems, this is more appropriate. Now, it comes at a high price, because my claim coming from the simulation world or code generation world is, if I have this, and then it generates Java, and I have to debug at the Java level, forget it, it's useless. If you give these high-level abstractions, you must give it all the way, testing, version control, everything. The rest must be hidden, like we have with hardware. When I run C code, it is translated to machine code, but the feedback I get, there's a symbol table there which tells me at that address is variable X. I get feedback in my debugger at the level of my program code. Yeah? If we go to DSLs, we must do the same. Yeah, so it's not a black and white story.
I always found the one you mentioned.
Yeah.
Domain-specific in the trenches. So Google.
Yeah, and so what is his name? I forgot his name. I have the reference somewhere. Yeah, okay. I like state charts, hence the answer to my question during the PhD defense of Joachim was state charts. But I think the question was something, if this and this and this is your context, what is the most appropriate formula? And the answer was state chart. Now, okay, I want to model a traffic light. I have this timed automaton. And of course, and you see, it is there, the answer to your remark, most appropriate. Ultimately, you have to do empirical studies. Yeah, because it's the same with Moody. Moody has his rules, but ultimately you have to do empirical studies because it depends on so many things, the background of the people and so forth, the context in which you use it, evolution. That was another paper by the guy whose name I can't remember. They showed that, and I think this is something we discussed earlier today, that is, a domain-specific language has some concepts, a very limited number of concepts. And you combine them in different ways. And of course, for code generation, typically each of these corresponds to a bit of code that is already in a library. Yeah? And I make changes very rapidly, push the button, I get a new implementation. So wonderful. But what if the language changes? And there's a problem, because maybe the language, you have breaking and non-breaking changes. It may be that my old models no longer conform to the new language. And so this study, it's on the tip of my tongue. The study that was done at Panasonic showed that typically you keep using your domain-specific language. You evolve it in an additive way. So all the old models still work. You don't remove anything, you don't break. But you always have a Turing complete escape hatch. You allow a block in which you can put arbitrary code. Now the problem is, over time you see that that block becomes bigger and bigger, and 80% of your solution is in that block. That's the time to take a step back and say, oh, but what are the concepts there? And maybe I have to evolve my language, and these now become domain-specific blocks. But there's this whole story of how to evolve this, and that's where you pay the price for domain-specific language. Evolution is a tricky one. Now, why do I show this? I actually, when I teach state charts, I used to ask my students to write code using threads and timers and whatnot, to write code for a traffic light. The results are interesting. And then I give them state charts. I explain state charts. We now use Yakindu. We used to use our own compiler. You push the button and out comes your solution. As Edward Lee says, threads are evil. We are not made to program with threads. We are made to reason like this. So you could argue that this is more usable by humans, and the rest should be done by a compiler. And so this is my hypothesis. I do a small modification in the model, I regenerate my application. Or here I do a small change in the model, I regenerate my application. If the application is code, if the distance here is small and the distance between the code at the code level is huge, the effort that I would have had to take if I did it manually would be enormous. And then it's worth doing domain-specific modeling. This is just an intuition. I have no proof for this. There are cases where a small modification leads to a small modification. I could have done it in code.
It may also be a sign that you're modular.
Okay, yeah. Okay, but I'll come to that next, because I am only talking about design now, but designs must satisfy requirements. And indeed, yeah. Okay. By the way, all of this is a multi-step process. This is in Atom PM, that same domain-specific model. You see it, it's not a commercial tool, no. So this is in my tool modeled. And then it gets transformed to an automaton, it gets transformed to a language to describe screens, and this is actually code level. And can you imagine, so I do automated transformations, ultimately I end up with code. What are the purple lines? Any idea? So there's purple lines all over the place. And they go from here to here, from here to here, from here, yeah. They are mapping, they are traceability links. Because if I want to write a debugger, because this is the code that runs, I need to be able to visualize it while it is running in my debugger at the level of my DSL. So I need traceability. So not only do you transform, but you actually have backward tracing information. And it is not necessarily a one-step transformation, maybe it's a multi-step transformation. Okay. My story is about appropriateness, it's not about DSLs. I'm not saying that DSLs are universally better. I'm just saying, think about what is most appropriate when you're solving a problem. Now, of course, that in itself leads to problems. As we will see later, all of a sudden, I have 500 different languages. Do I learn 500 different languages? Do I maintain 500 different languages? What if my one part of my system is best modeled, most appropriate in one language and another in another language? But what does it mean to combine them? So now I have that problem. At the level of Java, no problem. Everything's Java. So I'll come back to that later. And so there is no free lunch. But now we come to, it has to be right. The requirements must be satisfied. And so with Bart Meyers, who did his PhD on this, we called it promo box. It turned out to be more than pro and mo. Pro is property and M is design model. Property, design model, box. And Matteo Risoldi, I was telling you earlier, I was on his PhD committee at the University of Genève, and he worked at CERN. And he worked on something called the CMS tracker cosmic rack. And he had a domain-specific language. And from that, he would generate a 3D animation. He would generate all sorts of code, tooling. And his supervisor was Didier Boux, who is a Petrinet guy and who built something called CoOPN. He translated this to Petrinet. And then, if you have a PhD in logic, you can write LTL requirements, linear temporal logic, and you can use the CoOPN tool to do checking. And it either gives a witness or it gives a counterexample in a language that no one can understand. Okay. So, do you notice something? I like commuting diagrams. If this goes from domain-specific to something for analysis and to code and to, it's nice to have this domain-specific level and go to different, but here my property language is at that low level. The people who build this don't know Petrinets, they don't have to because it's automatically generated, but they don't know LTL. So don't ever ask me to be on a committee because the first thing I said is this is useless when he defended his PhD, because you're arguing it's a domain-specific language and then you force people to use LTL. So what is missing? There's something missing here. At that same domain-specific level, we also need a requirements language. And then, of course, you need tooling which does the transformation, which checks the satisfaction relationship. And if there is a counterexample, it lifts it and it shows it again using an appropriate notation. I'll give you the and so you see, this was then, it's the tool, it's called Alpina, the analyzer, and this is what you get as an answer. That's a counterexample. Good luck understanding this. I mean, what's the point of doing domain-specific modeling if ultimately you have to write LTL and this is the answer you get? I think this is useless. Okay, I was a little bit more polite during the defense, but he quit research after that. But he's now he works for one of these Swiss private banks, and he's a multi-millionaire doing stock market analysis. So things worked out fine. But I think he's still mad at me for saying that his work was useless here. Okay, Matteo. Now I'll give you a small example of Rommelbox. This is an elevator, and the elevator, this is my DSL. It's a very small and trivial DSL. This is the ground floor, first floor, second floor. On every floor, you can push a button. If it is pressed, it's shown, this is my visual language, it's shown in light blue. Here, of course, you can only say, I want to go up. On the top floor, I want to go down. And here you can say, I want to go down or up. And this is the actual elevator. The elevator is at a particular floor, not a very fancy visual notation. But there are 3 buttons inside the elevator. I want to go to the top floor, the first floor, or the ground floor. Okay. And I'm not showing you the semantics, but you can imagine there is a semantics which will then give you the dynamics given a certain initial marking and initial state, and it will start moving to honor these requests. And then I can ask, does it ever reach? Eventually, because maybe I have an algorithm which keeps going down and it never reaches the top floor, and there is starvation. So I can express this in LTL. What I'm expressing here is, if a button is pressed somewhere, either here or there, eventually, I'm not saying how fast, but eventually it will arrive. So starvation cannot happen. This is how I express it in LTL. easy to understand. At least I explained it to you in with a bit of hand waving. You can understand this notation. Not easy to understand. So then we thought, okay, we need a DSL here too, which will use sort of the same notation. What is that DSL? We have a universal quantifier which goes over parts in my system. Okay, for all floors O, doesn't matter which one. And then after, and then consequence, precondition. Eventually, it's a temporal formula. I could also say next, or it's a temporal formula. It is going to be translated to LTL. After on floor O, a button is pressed. It doesn't matter which button, up, down, X. It doesn't matter if it's pressed. Eventually, the elevator will arrive there. That's easy to understand, and it uses a consistent notation. And that gets translated to this. And now, of course, we can use our tooling, but we're not finished. What if this is not satisfying? Then typically a model checker will give you a counterexample, a trace. So I not only need a design language, a property language, requirements language, I need a trace language. And that will be snapshots. This is a snapshot. A next snapshot, maybe that line will move here when the elevator moves up and so forth. So I need a sequence of snapshots. And so this actually leads to a design language, an input language, a runtime language with the current state, a trace language, a property language, and of course a description of the semantics. So you need all of these languages, and they're all domain specific. And they get translated, that gets translated to LTL, this to Cromela, spin is used, it gives a counterexample, which we then show as a trace. And of course, we've applied this in different contexts. You could do this with differential equations, you can do this with different things, different domains, but the principle is always, I have a collection of languages which are intimately related, and I need all of them. And then behind the scenes, of course, I have all sorts of lower level technology. And you can, of course, when I go back to this here, you can imagine having again a language which matches this. Okay. So we call this promo box, but I think this is very similar to what you are doing, but you do it with templates. Huh?
I'm just wondering the property language.
Yes.
Because in this example, for instance, for the escalator, for the elevator.
Yeah.
Eventually, we will have
the
elevator, but to get there, the property is more complex than just this, because eventually I need to have it, but if the elevator goes up and down more than 3 times, and that's still waiting.
It all depends on
optimal. So
it depends on the semantic domain. For example, there is STL, single temporal logic. Okay. In single temporal logic, there is a notion of time intervals. Okay. So in other projects, we actually typically with industry, we map onto STL. Okay. And STL is much more expressive. The problem is the static model checking may not work. So all we can do is we synthesize runtime monitors. And all they do is they sit there in your real-time system, and they give an alarm if something goes wrong. So it's this trade-off. So yes, it is again, what is the most appropriate semantic domain for my requirements language? And in this case, it's actually a blend of a structural language for all elements and a temporal language. So there, well, yeah, in
what I mean is that this formula here is not really represented by the little example.
You mean this?
Yeah.
Yes, it is.
Yeah.
Because you see, the for all is actually by repetition. Floor 0, floor 1, floor 2, and so forth. So because LTL does not have that structural part. So we expand. That's why it's so large. And then the temporal part is there again and again and again and again. So it's just an expansion in this case. Yes. This is actually automatically generated from this. And it's the same.
And actually, I wanted to add that there have been some like template-based languages that were proposed specifically that are like when you read them, they are pure natural language,
Yeah.
and then they are automatically analyzed to LTL.
Yeah,
So there have been some.
Actually, even what we did with Bart in his PhD was actually as I said, there is this collection of languages. What we actually do is we have one super language, and it's sort of a template language. And then from that, these individual languages are generated, because you want these languages to be consistent. This language and this language, they must use the same elements. One way of doing this is to check consistency. Another one is to have a super language, the union of all languages with some tags, and then generate each of these. Of course, this is templates at another level. Your templates are basically at this level. Yeah? And I'm talking about here. Yeah.
Just a point of order. This is fascinating.
Yeah.
And the time, and I think I have
We
reached
should
one.
bring you back for
Yeah.
like a tutorial, 2 or 3 day tutorial.
Yeah. So I don't know. I
See what you can.
maybe I can
Like the next
without
slide.
going into any detail.
Without asking
I,
questions.
And yeah, I mean, this is fantastic. I mean, thank you so much for
Yeah.
your very pertinent question.
I was
This is
gonna say earlier, if it's interesting or not, well, if it is interesting, people will ask you questions,
Yes.
and then it's gonna take long.
And
Yeah.
there were plenty of questions.
Yeah,
It must be
plenty of
interesting. Yeah, okay.
It's very interesting.
What you don't want is that you go through your slides, any questions, no questions, any questions.
And if you want
Have
checking the-
some coffee. Yeah.
Yeah. Yes. Okay. So remember the title of the talk is most appropriate. So I've gotten to number 0.
Yeah.
Number 1, number 2, but there's a few more. Appropriate abstraction, appropriate notation, formalism.
Semantics.
Yeah. I'm now going to go very quickly through the remaining ones. And don't ask questions. You're not allowed to ask questions. Okay, so I've said this a number of times. In the real world, if you don't have appropriate tooling, documentation, versioning, execution, monitoring, debugging, if you don't have tooling that works at the right level, industry is never going to use. Yeah? So this is something which I try to stay honest. When we build something, we try to have support for debugging, we try to have support for versioning and so forth, because without that, it would be dishonest to go to a company and say we can solve your problems, because you will give them even more problems. Okay, now I mentioned it, combinations of formalisms. For example, this is the power window which we built, and we have state charts, we have differential equations and so forth. Wonderful. And actually, this is a commercial tool. By the way, this is not what we built. We also built something similar, but this is a MathWorks tool. State flow, sim mechanics, and so forth. Yeah, I've lived the dream. I've used the most appropriate formalisms, and now I connect. What does it even mean to connect an automaton to a differential equation? What does it mean? Okay. And you see this is state flow component. This is sim mechanics component. So in essence, we have a network, an architecture with 2 models in formalism green and 1 model in formalism yellow. What does it mean? The answer is, I'll bring it to something, to a level where I understand what it means. So one possibility is, and Vangheluwe calls this the fragmentation problem. My answer to it is to draw a formalism transformation graph. What is a formalism transformation graph? I'm going to draw a graph where the nodes are formalisms. The formalism green, the formalism yellow. And I'm going to show that, for example, I can translate state charts. This is the blue arrow. I can compile it, translate it to a formalism called depth. And I will preserve certain properties. Actually, I can even go from differential algebraic equations. I can go here, but I'm crossing this great divide, which is, it's no longer exact. This is continuous, this is discrete. So here I do an approximation. But now it gets interesting. I take a state chart and I take GPSS or so, I take some discrete event language. I translate both of them to the common language devs. And now I no longer have green and yellow. I have green, green, green. Everything is devs now. Huh? And it preserves properties. And then maybe the formalism devs is quite modular. I know what it means to combine in a hierarchical way, green with green with green, devs with devs with devs. So that's one possibility. Yeah? Of course, each of these, I put it here, each of these blue lines requires an entire PhD to prove that the properties of interest are preserved. Because you can say, I translated and I wrote a compiler, but you have to prove that it is semantically equivalent with respect to the properties of interest. So not easy. Okay, that's what this whole thing is here, what I did in my PhD a long time ago. But you also see that instead of these blue lines, I have these green lines. And they take a partial differential equation, a differential algebraic equation, a state chart, and they simulate it. And they go all to one level, which is traces. Which is okay, of course, if I only have state charts, I produce traces, simulation traces. But what if I have multiple? I could actually do the combination of the green and the yellow. Maybe I have a green simulator and I have a yellow simulator, and they both generate traces. And now I orchestrate at the level of the traces. What do I have? Co-simulation. I have an orchestrator, but of course, here I have the advantages of symbolic analysis and explanation and optimization at each of these levels. Then you lose that. And that's the problem with FMI, for example, co-simulation, they're black boxes. You may get inefficient, incorrect results. So this subsumes both the white box transformation to a common formalism and the black box orchestration. Okay, and that's what you see here. That's another lecture about FMI. Okay, combinations of formalism. We also have embedding. Yeah, this is a hybrid model which combines automata with differential equations. Thank you for your nice questions, and I apologize for
You're not asking more questions. I have to give.
Yeah, now things will speed up. Now
I
that
have
you're-
another meeting.
Yeah. Okay, so I can also do some combinations of languages actually make sense. And then, of course, you see this hybrid behavior. Okay, I lived in West Virginia, and they had in Morgantown, West Virginia, they had this personalized rapid transportation system, and that's where I modeled this. In most appropriate views, I may have multiple views on the same thing. This is an architectural view on a home automation system or on a video, audio, whatever system. But of course, each of these ports, this is a network connection, each of these ports carries packets. There's a protocol automaton describing in which order they are allowed to arrive and so forth. And there is a standard about multi-viewpoint modeling. And we need consistency. And now we come to consistency. What is consistency? We often, there's a lot of misunderstanding. I have two design artifacts. These design artifacts, maybe they are at different levels of detail. Maybe they are different components. The thing is, maybe I can analyze some properties. This is the set of properties, many, many properties. With this design artifact, I can analyze all these properties. With this design artifact, I can analyze all these properties. Safety, energy efficiency, and so on. Of course, if I have a property that is only analyzable through this artifact, this model, consistency has no meaning. There cannot be a conflict with an analysis using that one. But if we are in this region, where there are properties that can both be reasoned about by doing a model checking or simulation of model 1, model I, and model J, then there is maybe inconsistency. Inconsistency would mean that this is, let me see. This is the region of satisfied. So let's say that I do an analysis, and for a particular property, we see that it is by analyzing DI, it is satisfied. And by analyzing DJ, it is also in the satisfied region. So both of them agree. Here, both of them disagree. Both of them say it's not satisfied. So they are consistent. But here they do not agree. And that is inconsistency. Now, the misunderstanding is that we must do consistency management. That is just a heuristic. Because maybe I can keep inconsistency around for a while. That doesn't guarantee that my end result will be correct. It helps me towards it. And ultimately, eventually, all my artifacts have to be consistent. But it is so we have a Journal of Computer Languages paper, model consistency, as a heuristic for eventual correctness, trying to explain what the essence of consistency is. And it's this. And you can have horizontal consistency, vertical consistency, and so forth. Okay, so we need to explicitly model workflow. And now I'm really speeding up. This is my formalism transformation graph. This is a workflow model. When I go to a company now, I ask them, which tools do you use? Which formalism do you use? What is your workflow? I'm trying to chart what they do. And then we can see whether they use the most appropriate language, where they can optimize their workflow. So by modeling workflow and modeling which languages are used, you can really learn a lot about their engineering practices. And of course, we try to build tooling for that. And yeah, okay, this is about digital twins and about different iterations. We're trying to design a line following robot. And of course, the first one doesn't do it at all. The final one does it. You need to record all your intermediate artifacts so you have traceability. Why did I do it this time, this way? Because I built it like this before, and I built it like that, and that didn't work. So you need traceability. And so for that, we use language models, we use our formalism transformation graph, we use process models of our engineering process, we use traces, and we use some federation where we do use commercial tools and we somehow orchestrate them. So I'm not going to go into detail, contracts and so forth. I'm just going to say that traceability between the experiment I do and my system, between versions, between properties of interest, between levels of detail, between instances and types, and then fine-grained traceability between elements. Yeah, okay, no time for that. For example, Alexander Egiet has this tool called Design Space, which keeps different views consistent. And more generally, this is a tool called Syndea for keeping simulation CAD requirements, Doors is there also, keeping them somehow linked and consistent. So more and more, this is Sylvain, who at some point developed OpenFlexo, which again is a federated architecture to keep many, many different things linked. And of course, what is the challenge? Both these tools, they just keep the links. But we have to give meaning. Is this an abstraction relationship? Is this is an experiment result? This was the context, that was the system, these were the requirements. All of this, how do we do this? Actually, the way we do it now is to have an ontological layer to be able to reason about all these relationships. Okay, and I think that's, yeah, even, so Itemis is the ones who build, among other things, the state chart modeling tool Yakindu, but it's called Itemis Create now. But they've also gotten into knowledge graphs, so this is my segue into ontologies. Safran, you probably know, a big French company that builds jet engines or designs jet engines. They've actually been using this FTGPM, the charting, the formalisms they use, looking at their workflows and trying to improve. So there are some companies that actually use this. I think the future is we need to manage everything. Well, okay, the real conclusion is most appropriate abstraction, level of detail, formalism, viewpoint, and so forth, most appropriate. But my vision for the future is what I call the modelverse, the universe of models. We need to manage all our knowledge, be it raw data, measurements, be it differential equations, be it whatever, in some kind of graph. A big challenge is this will constantly be evolving, not only the data, but also the models and even the languages will evolve. So how do we deal with this? I think twinning, and note that I don't call it digital twin. Twinning is a broader concept. We will have an ecosystem of twins. Every object in the world will have a twin at some level. That will be a way of supporting evolution at different timescales. We should combine what I call linguistic modeling, which is the traditional meta-modeling, modeling, semantic mapping, with ontological modeling. And in engineering, we've been doing this forever. We are not just simulating, we're also going from data to structure. We're finding patterns, we're estimating parameters, and so forth. So the data-driven way is this, the deductive way is that, and it's the interplay between both that really lets us solve complex problems. And I call all of this multi-paradigm. Okay, I rest my case. And I was speaking here, I hope. Did anyone say that they couldn't hear anything, or they all left?
I think there is one question. There is one person with their hand raised.
Okay, good. Yeah. Is my audio on? Yes.
Thank you very much, Professor, for this talk. My first question, I'm sorry, I have to ask this stupid question first, but is your last name pronounced something like Vangheluwe?
Vangheluwe, yeah, that's very good. Yes, it's a Flemish last name, yes.
And you mentioned earlier the formalities of defending doctoral degree in different countries.
Yes.
There's a paranymph in the Netherlands once at Utrecht University.
Yes, yes.
That's interesting. You know about that, of course.
Yeah. There are usually two paranymphs, and if the candidate faints, the paranymphs can take over. And yes,
There's all sorts of legends about what they can do. That's true.
Yeah.
Yes. Thank you very much for this presentation. I did my doctoral work consisted rather of a simulation of neural networks. This is back in the late 50s, and all these modeling questions came up. Of course, we didn't have the vocabulary or many of the concepts that you introduced today. But I'm very intrigued by this, and I'm looking at your conclusion here about the model verse. First of all, it's going to take me an hour or so just to understand what that means. I'm very impressed by that. I'm also interested in languages and a theory of languages and models for languages. And the models I'm looking at, grammars, for example, tend to be multidimensional things, and they involve actually they span not just the physical universe, but outside the universe, but they also span cognitive functions and human being itself. And so I'm deeply interested in that. So I had many questions to ask earlier, but my head is swimming from all this. One point you had a division line between what's acceptable, what's not acceptable. That's one of the early graphs.
Okay.
You talked about it on this side of this line, it's no good. On this side of the line is acceptable. I thought that line would be maybe a fuzzy entity.
Absolutely, yeah. And there was a question here about, is this really crisp? You can start using it. There are many ways in which it is actually not a very crisp line. It depends on the properties. It depends on the level of accuracy or fidelity you want, because maybe you're okay with a quick and dirty answer, or maybe not. And so maybe it doesn't have to be very accurate, or maybe it has to be very accurate. And so indeed, I've given a sort of very naive presentation of this. You can go very far in making this more fuzzy, in making this stochastic and so forth. But that's a separate lecture or collection of lectures in its own right.
I was very curious about unfortunately, missed part of your discussion about language towards the end, and the concept of multiple languages, infinite number of languages, dealing with infinities. As you know, we have models of infinities of order aleph 0, aleph 1, aleph 2.
Yeah. Yeah, some people say that in the real world, I mean, our computer world, that doesn't exist. No, of course, like real numbers have an infinite number of real numbers between any two real numbers. Of course, with our limited representation of numbers, this doesn't really make any sense. And you get, for example, Zeno's paradox. If I want to go from A to B, I first have to go halfway and then again halfway. But when I'm halfway, I then have to go halfway to the remaining halfway. And so I will never reach B. And this is a side effect of the way we've defined the real numbers. In reality, this makes no sense. No, we will always get there. So yeah, I think there are a lot of philosophical ramifications of certain choices of modeling formalism. But as it was Box, the statistician Box, who said, all models are wrong, but some are useful, which is sort of what I'm saying with my appropriate. Sometimes you can choose an appropriate language, an appropriate view, an appropriate level of detail to solve your engineering problem. And that's all we have, no?
Yeah. Well, I have to add just one thing that's maybe tangential to all this, but I'm quite interested in the implications of Bell's hypothesis concerning the taking two particles, separating by an arbitrary distance and changing what changes to one instantaneously changes the state of the other. And there we bump into a number of problems at that level of physics and the cosmological problems and the whole concept, for example, of time and space itself. We now think, there are model space that use Lie groups and things like that.
But you see, I have another, well, in my lectures, I actually show an example of appropriateness. When do I need to go to the quantum level? Is that appropriate? Where does this, from my engineering point of view, when does it make sense to reason about this? And it often does, actually. GPS uses relativistic. Tube lights are actually a quantum effect. So sometimes it makes sense. But of course, with your duality and with Bell, that is something else. This is then we're going to almost into philosophy. By the way, I'm very happy to answer more of your questions, but maybe offline, because people here are I think eager to finish the rest of the pizza and they have to get going. So thank you for your questions, and maybe we can.
Thank you very much. Vielen Dank.
Thank you very much, Hans. It was
yes.
Thank you for your questions. It was maybe a bit too ambitious. At models, I managed to go through this whole thing, because, sort of.
You weren't interrupted by questions.
And I was in the flow, and I don't know. I think I had to speed up also in the end, but and I had a bit more than an hour. You were one who fell asleep.
Yes.
But you had another joke. Yeah.
I'll maybe communicate with you.